electric field. So we introduced electric field in the last video. We said that the force that a test charge Q feels is related proportionally to the electric field at a particular point in space. So if we can calculate what this electric field is, then we can figure out the force that it feels. That's it. And this electric field is a sum over all of the charges that exist in my problem. Qi, Ri squared, Ri hat. Right, so that's the sum that was represented in the last video. All right, so let's go ahead and figure out exactly how to go ahead and do that. Right, we remember that this script R is related to the vector pointing from a source to a field. So I'll just map out the problem real quick. I have some point where I have a charge Q. Let's call that Q1. I have a point here that is where my test charge is going to be, or rather the area and space that I want to measure where the electric field is. Now we don't need a test particle anymore. We can just define the electric field at that point. Okay, I have a vector that points to my source charge. That vector is called R prime. I have a vector that points to my point in space. That vector is called R, and the vector that points between those is script R. All right, script R I, because that is the ith charge. So I know that to generate the electric field, to define what the electric field is, I first need to define what my R prime and R vectors are. That's the strategy that I use to solve these problems. Okay, so with that in mind, let's do example 2.1. Example 2.1 says that there is a plane. We are on the XZ plane. I have a test charge Q on each side of my Z-axis. Each one is a distance d over 2 away. And I want to know what the electric field is at some point P, which is a distance Z away. All right, now Griffiths right off the bat pulls a trick, and I want to not use that trick. I think it's better to just define, just go through a brute force before we start using tricks. All right, so I am going to have an electric field that's generated by both of my both of my source charges, rather. And from the left side, my electric field is going to be pointed in this direction. And I'll go ahead and call that E from charge 1, call that 1 and 2. And my right charge is going to generate a field that's pointed in the opposite direction. All right. And because my charges my charges on the left and the right side, Q1 and Q2, are equal in magnitude, I just labeled them 1 and 2 to specify that these fields were associated with them, but Q1 equals Q2 equals Q. Right, those are the same magnitude. They're the same magnitude, so they're generating similar looking electric fields. Right. And I know that my total electric field, right, which is my vector total, is related to a sum of all of my electric fields. And that sum is the sum over the vectors. The electric fields have magnitude and direction. Okay, so I know that I can decompose each of these components like this, and because of the symmetry of my problem, because both of my charges are equidistant from this axis, and they're of the same magnitude, I know that when I end up adding my electric fields by component, this will cancel this. All right, and then knowing that the net electric field is going to be in the z direction. Okay, so let's go ahead and prove that. So let's go ahead and do the electric field from one of these components first, or one of these charges first, and then we'll do the second one. Okay, so what I need to do to build my script R vector is figure out what my position vector is and subtract that by the vector that points to the field, the source charge. Okay, so let's go ahead and do the right side first. All right, the position vector for my point in space is always going to be 0 in the x-hat and the z in the z-hat direction. That's my vector notation for point P. That's associated with my r vector. And then my r prime vector becomes d over 2 in the x-hat direction and 0 in the z direction, right? Because it's on the x-axis. So that means that that vector is now minus d over 2 x-hat plus z in the z-hat direction. Right. Then, because I have a unit vector, I also am going to need the magnitude. The magnitude of that vector is d squared over 4 plus z squared. And therefore, since I have the vector and the magnitude, I can compose the unit vector, which is minus d over 2 x hat plus z hat. So I'm missing a square root there. Square root of d squared over 4 plus z squared. Okay, so now I can write E from the right. I missed some combining notations here, I apologize. So this electric field that's generated by the right charge is now minus d over 2 x hat plus z hat over d squared over 4 plus z squared, all right, times q times 4 pi epsilon naught on the bottom. Okay, that's not all of it. That was just the r hat. Now I need the magnitude on the bottom of d squared over 4 plus z squared. All right, that is the magnitude squared. Okay, so this is script r hat. This is the q over 4 pi epsilon naught, and this is 1 over r squared, matching this piece up here. Okay, so what's different about the electric field that's generated from the left side versus the right side? Well, I know that when I build my script R vector, I know that this component is going to be different, right? Because now my position for my new source charge is going to be at minus d over 2 in the x hat direction, 0. So anywhere that I have an x hat, I'm going to pick up a minus sign. All right, so then this minus a minus is going to be a plus, and I'm going to be left with a vector that is d over 2 x hat plus z in the z hat. All right, but that doesn't affect the magnitude. That doesn't affect the magnitude at all. So in the end, the only thing that's going to be different about my left charge is that this piece is negative. So I'm just going to copy this black expression on the left, but remembering that now anytime I see a d over 2 x hat, it's positive, plus z in the z hat, right? But on the bottom, it doesn't affect it because that was a squared quantity, right? So that's still d squared over 4 plus z squared q over 4 pi epsilon naught, same q, same magnitude, times 1 over d squared over 4 plus z squared. All right, so look, now you see that this expression, that part of the expression cancels with this part of the expression, and my x components cancel out just like we predicted before. And in the end, running out of space, I can add up my total electric field. These are just the exact same expressions, so I will rewrite it in compact form. 4 pi epsilon naught. That usually goes in front of the expression. I'm not sure what I was doing at the bottom. I'm left with 2z in the z hat over, and now I'm going to go ahead and combine these denominators. D squared over 4 plus z squared. That's the 3/2. All right, and that's the electric field from 2 point particles, and we know it's only in the z hat direction.